So it's my great pleasure to introduce Christian Szegedy. Basically, any famous paper that you come across in deep learning, any influential paper, you can find his name on that. I think the first one is Google Net. Then there is batch normalization, that without it, many of the methods in deep learning wouldn't work. And there is object detectors like single shot multi-box detectors. And then one cool fact about Christian is that he knew about some intriguing properties of neural networks, like the existence of adversarial examples back in 2011, but he never got to publish it, to write his ideas down until 2013 and 14. And what he's going to be talking today is even more exciting, about mathematical reasoning. So the floor is yours, Christian.
Yeah, thanks a lot for the kind introduction. So let me just switch to, so interrupt me at any time if something is really off. So I will talk about machine learning for mathematical reasoning. So this is a project at Google we are doing with a small team, where we try to apply deep learning methods to do mathematical theorem proving. So I will just introduce first what we are meaning by that at all. So, of course, there are all kinds of reasonings that people talk about. So, for example, if people think about AI-based reasoning, then often you think about AI answering some common sense questions. Like the one in the slide is that if a large ball crashed right through the table because it was made of steel, then it's not clear grammatically what was meant here. Is it the ball or the table is steel? But a human has no problem with this kind of ambiguities. Also, common sense reasoning is if you look at a picture, then you know what are the objects. For a human, that's not really a problem. For a machine, it's non-trivial to train a system that can partition the image into objects. So there are still there are other kinds of reasonings that are still fuzzy, but they are less reliant on like everyday experience or resolving ambiguities. Is the probabilistic reasoning when we just do like standard machine learning to give some estimations. So, for example, that if you have a chess position, then AlphaZero, that's a famous chess program by DeepMind, can estimate the probability of somebody winning the position. So that's based on probabilistic reasoning, where although the task is deterministic, it would take too much compute to make it efficiently computed. So you cannot really just assess the optimal solution. So you need to resort to some heuristics or even learned heuristics. What I talk about here is very different from the above two kind of reasonings, is mathematical reasoning. So for example, if you ask whether a planar graph is four-colorable, or every planar graph is four-colorable, then, I mean, there is a definitive answer. And the question is, if you can prove this question by creating a formal proof of it. So a formal demonstration, which was an actually in the 70s, but it's very, I mean, it's like these mathematical questions, they based on discrete reasoning. So they are not probabilistic at all, and everything is deterministic. So the question is, why would we want to use machine learning for them at all? So that's one interesting question. But the other interesting question that I'm also posing is whether we can at all create a system that reasons as well about mathematics as a human can. So how does mathematical reasoning differ from less clear-cut reasoning is that it's based on rules and it's formal, and actually basically what you have to create is create some input to a computer program that the computer program can verify. So that's what I would call formal reasoning. So basically, if you have like a logic checking engine in the computer, and you have to write a computer program that can create a demonstration, a witness for the truth of a statement. And every statement has a discrete truth value, either true or false, or of course it can be unprovable, which is almost, so every large axiom system, or like extensive enough axiom system has statements that cannot be proved, but if you can prove or refute the statements, then it's either true or false. And also the computations are deterministic. So once you prove something, you can trust that that statement is true. So you don't have like the different outcomes at different times. So what does mathematical reasoning, formal mathematical reasoning encompass? So one is that the one is interesting thing that most people don't think about is actually creating axioms. So that's part of mathematical reasoning. So you can have different foundations for mathematics, and your only goal is to have like a system that is without contradictions. So it has to be a sound system. And you can create different axiom systems, but they typically, if you have a sufficiently complicated axiom system, you can typically model other axiom systems inside that axiom system. So you can probably pick one that is big enough, or like not really, but that's something that's strong enough, and then you could actually formulate any other logics inside that system. So you have a lot of freedom how to choose it, but some axiom systems are just better suited for reasoning because they are easier to use. Also, deduction is an important part of how mathematicians work, is how do you derive new facts. And that's what most people would actually think if I would say automated theorem proving is just creating deductions, proper deduction steps. So you just formalize some statement first, and then you give it to the system, and the system should actually prove it. But actually, so mathematicians do work very differently from that. So a typical mathematician always creates new hypotheses, and then conjectures facts, and then tries to validate or refute those facts. So the way that a human works is that it studies the underlying objects, and then observes it, and then says, is this, can this be true or not? And then the question is, can we conjecture? So the question is whether my observation can be generalized to a certain extent. So that is induction, basically, but not mathematical induction, but just induction. So that you observe some fact. For example, you can observe how many prime numbers do you have that's smaller a certain number, and then you can get to the empirical observation that is kind of logarithmic, and then you have to prove it, and that's a much harder task. But you typically you do some observations and measurements before you come to deduction. And also a very important part of mathematical reasoning is concept building. So you want to create definitions that are easy to work with. Even if you want to model the same topic, you can model it very differently. So for example, Grothendieck, as a famous algebraic geometrist, told once that he doesn't like proofs that have any ideas in them, because he preferred that all the ideas are in the definitions. So if you make your concepts clear enough and the definitions are general enough, then suddenly most of your ideas from the proof vanish, and then everything becomes just like clear from the concept. I mean, it's a nice aspiration, but most mathematicians, I don't think, believe in that. But I think it still has a lot of validity. On the other hand, it's like that's a hard task, because if a system has to create new concepts, then it has to judge how well a concept is, how well a concept works, or how good is it, and that's a hard thing. So we don't really know how to create concepts automatically. So going back to these points, actually, one can even formalize these intuitions about mathematics. So it was formalized first by the famous logician Peirce. So in the 19th century. So basically, you have the skip case model that you have 3 different objects. One is the rule, the other one is the starting point as the case, and then when you apply the rule, you get the result. And if you look at these triplets, you can try to infer one of the parts of those triplets. So for example, you can, in deduction, you say, okay, I want to figure out what is the result of applying the rule. And that's a non-ambiguous problem to do typically, because if your rules are deterministic, then you can do that. In abduction, you want to infer the starting point. Where did you come from? So that's also important in mathematics. And then there is induction, where you don't know the rules, and then you try to figure out rules, and then you have your the limit is only your fantasy. So how far you can push this, and that's what mathematicians do most of the time, is to create newer and newer rules, and even rules about rules. So let me just give a bit of a background of what reasoning means in practice. So for example, the simplest kind of reasoning is propositional logic. So propositional logic, you have only variables that are true or false. They don't have any other, they don't refer to anything. So for example, in this case, you can ask whether this statement holds for any kind of input. So whatever you put in A, B, and C, true, so 0 or 1, so 1 or false or true, whether it always evaluates to true, this expression. And so this is it looks very extremely limited, and of course, so this is far from doing real mathematics, but this is extremely useful in chip design actually. So you can formulate a lot of the chip working correctness of chips by propositional logic, and then people use set solvers to solve such statements. So they prove either that something can never be satisfied, or so there is no substitution into the variables that it evaluates to true. So that means that if you can, so that means that your chip works. And if you say, I find some substitution that for which statement is true, then the chip doesn't work, because typically people formulate that property that something goes wrong with the chip, and then they verify that that cannot happen. Okay, so that is very limited, and actually it cannot argue about anything that is infinite. So it cannot even argue about integer numbers. Here we can go to a bit more complex logic, and that's, I mean, much more complex logic. That is the first order logic. So in the first order logic, you have a clear domain of variables. So for example, X can be natural numbers, and you say that for every natural number and every other natural number, you have a commutativity law, for example. But they could have like different types of objects. So for example, you could have sets. So for example, you can formulate most of set theory by first order logic. So the axioms are actually first order logic, but there is a caveat in that. So if you try to formalize the Zermelo-Frankel axiom system in first order logic, then you end up problems with some of the axioms. So some axioms say that for every formula you have a set that consists from those elements for which the formula holds. So that's the that you cannot formulate that axiom with a single axiom. So you have to create an axiom for every formula if you want to create a first order logic formalization of the Zermelo-Frankel axiom system. Another example is that the principle of induction. So for example, you say for every proposition, if the proposition holds for a number, and if it holds for a number smaller than all those numbers, then it holds for the next number, then the formula holds for every number. And of course, so this also depends on which formula you want to use in that induction. So and it holds for any inductions, any kinds of inductions, but it's still or any formula, but it doesn't you cannot really formalize this statement with a single axiom in first order logic. So that's a huge limitation of first order logic. So the way that people got around in computer systems that use first order logic is that they allow for axiom schemes. So you say, okay, I can index axioms with other formulas or other functions, and then it becomes a mess because then you have to figure out, okay, what does that mean exactly? So you basically you still extend your logic a bit, but you try to stay in the realm of first order logic, which is possible, but it's hard to create a system that works consistently on that basis. So what people do instead is that they use higher order logic. So higher order logic is a logic in which you can create quantifiers over propositions and functions and some formulas in general. So you can say that for every function f is commutative if this holds, and then f can be really a function here. So this might not show the exact power of this, but I could have shown, for example, the induction hypothesis. You can imagine that, for example, the inductions, the statement that if some proposition holds, then you quantify it over that proposition and say for every proposition holds that if it holds for 0 and you have the implication, then it holds for every number. So then you are also quantifying about every proposition. So this means higher order logics tend to be like more powerful, so you can formulate much more things. But the problem is that they are much harder to automatize than first order logic, at least traditionally. But still, people who try to formally prove theorems, they always used higher order logics because higher order logic was much less cumbersome to work with. So it matches our intuition very well on how it should work. But there were no theoretically proven nice algorithms to do anything really useful for higher order logics before. And this is really changing with deep learning now. So let me just talk about a bit what are formulas in general. So formula is basically a tree. For example, you start with a sequence representation of that formula, and here the exclamation marks means for all. So that's a way that typically people in automated theorem provers, they denote the for all quantifier. So it says for all x equals x. So that's a simple reflexivity axiom about the equality. But I mean, if you turn it into a higher order logic formula, then the higher order logic requires that every part of the formula is well typed. So we also assign types to the part of the formula, and the formula becomes much more complicated than it looks on the paper. So you get actually points like there is application parts and there is lambda expressions. So these are functions that are unnamed functions basically. And then you assign to every constant, at least you have to assign, and every variable you have to assign a type. And in this case, your x equals x is a function that maps any type. So the for all has a type that maps any function that is a proposition to another Boolean value. So the details don't matter that much. So what I really would like to highlight here is that you end up with a tree. But these trees can imagine that this, I mean, you have a somewhat moderately complex formula, then your trees become really big. And when you grow it even further, then your trees become really, really big. So you start to prove something automatically, then your program generates all kinds of intermediate formulas, and those trees corresponding to those formulas can just repeatedly have the same type everywhere or the same subterms at a lot of places. So what people instead do is that they merge all the subformulas to the same node. So whenever something happens, so for example, in this part, you can look at the two types, and you can notice that the two types are very similar. They are not exactly the same. So you can merge at least the function that maps A to a bool and then you end up with a much more compact representation. So in this case, it doesn't have that much because its formula was relatively simple to start with. But if you have a somewhat more complex formula, then the saving can be huge. And also that helps us to create like much more efficient representations of mathematical facts. Okay, so how the deep learning enters the picture, and now so I know I start a bit like maybe a bit too fast. So the idea here in deep learning is that you want to represent the whole formula with a single vector, a fixed side vector of numbers, real numbers, really. And the way to do that is that you run it through some ad hoc created functions, and that function is, I mean, it looks kind of complicated in most cases. Some of those functions are relatively simple. So I don't really have like slides about the basics of neural networks here. But imagine that you have a computer chip, but you don't propagate bits in your computer chip, but you are propagating real numbers between 0 and 1. So, for example, if you look at these LSTM networks, then they are continuous relaxations of the latches in a computer chip, and then you run through your network. And the question is, what controls how that chip works internally? And the control logic inside that chip that decides which signals should be passed through, let through, are controlled by matrices. So these matrices do some pattern matchings on the input. So imagine that you don't just relax the computer chip to 0, 1 numbers, but you restrict it to actually vectors. And then these LSTM networks, they work like latches where you have the control signal that decides when something gets overridden by the input. Is decided by some matrix that matches the input and the content of that memory cell, and then decides whether it should be overridden or it should be kept, or the input should be dropped. So basically it works kind of like a finite state machine. But you are learning those matrices that control the finite state machine. And so that's the way that you do that in a recurrent neural network is that the control logic for every cell is the same. So you are sharing the matrices between these blocks. And then the question arises, of course, okay, so it's nice that we have all these matrices and they are kind of like ad hoc functions here. And then we encode our inputs as vectors. And then at the end comes some vector representation that encodes the whole formula. But how do we learn how this should actually, so what should be those matrices? And there comes the really amazing things about deep learning is that I'm still amazed that this works so well, is that you can just pretend that this function is easy to optimize, which is absolutely unclear. So for most people who would just like start doing deep learning, or 10 years ago, most people were extremely skeptical about this. And the funny thing is that just say, okay, just put an objective function that we say that this neural network should produce the expected output, and then just train the whole thing as a long network of layers. And then somehow this works. And it didn't used to work very well before 2010, but the reasons for that are kind of disputed by many people. So some reason that it didn't work that well is that they typically focused on functions that were harder to optimize. The other reason that it didn't work that well is that they didn't have the compute power. And the third thing is they didn't try it on large data and large enough functions. So it's a bit paradoxical, but the bigger your networks become, the easier are they to optimize somehow. So for example, if you try to create like a toy version of this problem, then it would hardly work. But if you say, okay, every vector should have at least dimension 1000 here, then suddenly the method works much, much better. And nowadays, people try to train networks with trillions of parameters. Okay, and actually there are papers about how everything scales up, and they not just. So the another paradoxical statement is that if you say, if you train a network with trillion parameter, you would expect that it would overfit badly because you are fitting a function with a trillion parameter. Then why doesn't it just memorizes all the data? Like if you have learned in basic mathematics class that if you fit a function with only a few variables, then it relatively smoothly approximates your data. But if you have like your degree of your polynomial gets too big, so they have too many parameters, then it just it can arbitrarily fit your data. But strangely enough, in deep learning, if your network is of the right shape, then the more parameter you have, the less overfitting you have. So that's a very strange phenomenon. Whatever. So there are newer networks. So this RNN is actually from the 90s, but for a long time it was not really used because of like limited computing resources. But they got really popular in the 2000s, and now people migrate away from them because the current most efficiently performing architectures work on a somewhat different way, that you are trying to match not just with the cells. So this architecture works in a way that you are always trying to, it's like a chain of fletches or a memory cells that just updates itself regularly with the same rule. But current architecture works in a way that every cell sees everything before. So that makes the whole architecture much more expensive, but to evaluate, but it's easier to train. So I will give a more mathematical slides on how this works. So let's just go over this. So there is another idea that people used for a few years, and it's still kind of popular for representing formulas and graphs, especially for example chemistry in molecules, is that you create graph neural networks. So the idea is that you, for every graph that you encounter, for example, this graph that we have seen for the formula, you create a neural network that represents the where every node is represented by some small neural networks, and that gets information from all the connected neural networks, and then you are doing multiple steps that passes information through these neural networks. So basically, every neural network communicates its in neighborhoods outputs, and then you're doing like a certain number of message passing rounds between these neural networks. And then you create, when you train this neural network, you have to unroll the whole thing. So you are basically duplicating as many times, as many passes you want to do. And for example, we are doing like 12 or 16 passes. That means that your network has like 32 layers if each pass takes like 2 layers. And or it can be like 4 layers, and then you have like neural networks that have 100 layers, and then you optimize the whole thing with gradient descent. So that's still very popular, but I think that the transformer network starting to outperform these graph-based networks. And the other drawback of this is that the data is, you have to create neural network for every input, and that's very inefficient on modern hardware. The modern hardware works best if your data is uniform. So for example, GPUs and TPUs, that tensor processing units that Google uses, that were developed for this particular purpose. They work only very well if your matrices are big and everything is very homogeneous. So these graph neural networks are not that efficient with modern hardware. So the idea is that instead of representing it with the graph structure, we just throw the whole thing into a so-called transformer network. And I will give a small overview of what is a transformer. So it's basically you have a matrix that computes key for every every memory element. So basically, for everything you have seen so far will receive a key, but that key is computed by a matrix. And then everything you have seen so far will receive also a value. That value will be created by a value matrix. And then in the current step, you are also computing a query matrix. So you are querying everything you have seen so far. And the trick is to make the whole thing continuously differentiable. So you're applying a so-called softmax function, which after comparing every key with every query with every key, after you compare every key with your query, you're looking at the results. The results are arbitrary real numbers, and then you apply softmax. And then softmax turns the whole thing into a probability distribution. So it will become numbers between 0 and 1 that sum up to 1. And then you weight all the values with that probability. So basically, you are computing the probability of needing to update a certain previous element. And in order to not just do it with a single matrix, but so you might want to retrieve multiple previous elements. So you are replicating the whole this whole process multiple times for every step you are making in your recurrent computation, and that gives you like multiple lookups in every step. And then you stack the whole thing several times. So it's a relatively expensive procedure. But nowadays, neural network hardware starts to be tuned for that purpose, so it's not that crazy anymore. So typically, you having like in every step, you have like 16 lookups, and then you have 16 layers of these 16 lookups that feed into the next layer. And that happens for every input that you are processing. So every input, you're doing this 256 kind of lookups for all the previous computed numbers. So it's kind of crazy. And that's a very, very influential paper, and probably that is, I mean, it's behind almost every magic you see today in neural networks. So, for example, OpenAI's language models are based on the exact same network architecture. So well, this slide just shows what I just stated, what I told, that this whole thing is replicated at multiple levels. So, and the way that that these language models work is you typically you are omitting something. So another trick is that my presentation is a bit more tuned for this like an audience that knows machine learning pretty well. But so these neural networks can be used in various ways, and the most interesting way that these neural networks can be used is the so-called unsupervised training. So the idea is that if you, for example, feed in a sequence in your neural network, then you can learn the distribution of all the sequences without having any targets for them. So for example, you can feed in the whole Wikipedia and then try to predict the next character, independence of how of all the previous characters that you have seen. So that's a traditional language modeling that was done for 20 years. Is that basically you're learning, factorizing a probability distribution of all the possible natural language sequences, for example. In our case, we can also learn to represent mathematical statements with the same idea. So a newer version of this idea is that you don't predict the next statement at every point, but you are dropping out a certain percentage of the tokens or characters, typically tokens, because characters are much easier to predict. And then then you're trying to predict the missing words from their context. And that's the so-called burst type pretraining. And that pretraining is basis of a lot of natural language processing results nowadays. So it basically birthed language model is just a transformer with the same idea. There's the exact same architecture as in this slide, but it is pre-trained in a way that they took a lot of natural language text, and then they dropped out a random 15% of the words, and then tried to predict those 15% of the words. And then they train it on a lot of data for billions of tokens for days, and then after that they can fine-tune the network. So they take a task that has actually a supervised output, so that they say, okay, this task is something that I have to solve. For example, you say, I want to solve sentiment, for example, the sentiment of a movie review. So I want to decide whether that review is positive or negative. And then, or any other review. So for example, that's one task, or you can do question answering with it. And then those tasks are supervised, so you don't have unlimited data for them. So you take the network that was already learned how to produce natural language, how to process natural language, and then fine tune it. So you're taking those matrices that work relatively well, and then you apply another optimization step that optimizes your real objective, but starts from that starting point. Okay, so that's a very interesting question. How can we do pre-training that is suited for mathematical modeling? And the idea is here is a slight modification that you say, okay, I don't drop words. We are dropping subtrees from the formulas. So this is a paper with from Google Research. Is that we took a lot of formal mathematical statements in formal description, and then dropped subtrees from them. And then the task of this neural network is to create, using this next token prediction idea, we're trying to predict the whole sequence of the missing part of the formula. And we just use the same transformer network that everybody uses in natural language processing. And interestingly enough, when you do this, okay, so you can do this one. So there is another important task in I will come back to this point. There is a supervised task that we are most interested for natural language, for mathematical reasoning, is the supervised learning of how to do deduction. And what is deduction? So deduction typically starts with a goal statement you want to prove. And then we have a database of statements that you want to look up from. So for example, you can have like 1 million statements that you already proved. And then there are certain inference rules. So let's say they're not too many. So there are a few dozen. And then your task is, the hardest part of the task is, okay, you have to find the inference rule, but most importantly, you have to find what statement to use at that step. So you have to pick the parameters of that inference rule. And in order to do that, you have to train a retrieval model. And how do we do retrieval? We just train this language model style model that embeds the whole formula as a vector. And then, okay, so maybe I don't know if I have it. Yeah. So here is a semantic. So schematics. So you start with a goal, and then you embed it to a vector. Then you look at all the potential premises and then embed it with a vector. And then you apply a really small combiner network. You could even just use scalar product here between the two vectors. And then let's imagine that this is a scalar product, but it works much better if it's a small neural network again. But with scalar product, it's easier to see how it can work, because the trick here is that you don't have to compute this vector for every. So you don't have to propagate through this neural network for every pair of goal and premise. You can pre-compute the right-hand side. And then you just embed first all the premises into a vector, and then you just have to run the neural network for the goal only. And then you do a scalar product, and then look at, okay, a matrix multiplication basically, and then you say, okay, which one is closest, which one matches my goal best. And the two networks are not the same, the goal and the premise, so it can also capture asymmetric relationships between the goal and the premise. So you don't get the same result that you say, okay, I mean, it wouldn't be true that if you have like a premise, if the goal would like to use the premise, that's a very different thing from the premise wanting to use the goal. So it shouldn't be symmetric, and it is not. So that's an important trick. And the question is, of course, what kind of networks? What is the embedding network for the formula that computes these vectors? And there you can use LSTMs, you can use graph neural networks, or you can use transformers. And for a while we used graph neural networks, which worked very well. But now we started to use more transformer-based solutions, and we are migrating much more to that. Also, you can even use convolutional networks in that sense, which is was more developed for images, but it works pretty well in that respect. So once you have this, then you can create a search process that takes a goal, it applies some inference rule, creates another goal, then it looks at what goals it has, then looks at which one is the most likely to be proven, and then picks that goal and then searches. So you can do breadth first search, you can do Monte Carlo tree search, you can do just beam search, whatever. And then each of them gives you a theorem prover. So the drawback of this process, though, is that it never really can create any statements for you from nothing. It will always create statements that you deduce from already true statement or conjectured statement, but it will not conjecture you anything. It doesn't observe the semantics of that statement. So the whole thing is really purely deduction. It's just search for deduction. I mean, it might sound limiting, but 99% of automated theorem proving is just about creating such search processes. And traditionally, automated theorem proving was extremely poor at creating induction invariants or guessing things and making up conjectures, because people didn't know. I mean, that there was no way to do that before. So basically, the way that it works is that our neural networks now models how a human would do the proving, not just like a search process. So here is a proof search tree that I just demonstrated. So you can see that there are a lot of branches where it just stacks, but it often finds passes. And actually the proof can branch, because, for example, if you have like an A or B statement, then you have to prove or not. So if you have an A and B statement, then you want to prove A and you want to prove B. So you get the different, again, you have two goals and you have to prove both of them in order to prove your statement. So your search process can be a bit more complicated. So coming back to the problem, so previously it was extremely hard to create induction invariants and new conjectures. But what we tried is that we created this process that we looked at all the proof steps in proofs that humans have proven with this automated theorem proving system. So there is, for example, a large repository of proofs that humans did for years. So that was like a 5 years long effort to prove the Kepler conjecture, which is a famous conjecture in, or not statement, or proof or theorem now, and it's Kepler's theorem in discrete geometry that comprises of hundreds of thousands of intermediate proof steps. And this was like it was a multi-year effort by 20 people who were doing that formalization manually. And we're using that repository to train a language model on all the intermediate steps. And then we mask out random subtrees from them and then try to predict what is the missing subtree from that formula. And interestingly, if this task is already, you don't even have to fine tune. When this task, you can actually formulate a lot of interesting tasks. So for example, if you want to solve the task, what is the premise that I need for a certain theorem to hold, then you can formulate it as a skip tree task. So you are just removing that subtree that describes the premise, and then ask you, okay, predict the premise for me. So that what do we need in, or not the premise in this case, it's an assumption. What assumptions do I need for this to hold? So, or you can even ask. So, for example, in this case, this shows what is the ground truth. So you need certain kind of statements to hold on the left-hand side in order for the right-hand side to be true. I mean, there could be a lot of stuff. It's always the case that if you just predict false everywhere, then this would be a trivial task. But the neural network was not trained on data that's seen false on any of these implications, because it looked at real formulas that arise from real tasks. So it learns what the humans typically have here. So therefore, so it's a very unspecified procedure, because it really just learns what humans do. It doesn't really have to. You cannot formulate why it just predicts a reasonable assumption. It really learns it. It just develops the intuition. Also, another interesting task that you can formulate it as a skip tree task is predicting the right-hand side of an equation. So, for example, if you say you have this on the left-hand side, what is the right-hand side? Or vice versa. But typically, the right-hand side is more interesting because a humans write in that order. So, but yeah, so and then there is also an interesting task is to predict the type of certain subformulas. So that's not really hard, because type inference is a relatively easy process. You can prove it, but still, you can measure how well your neural network is doing on type inference. So you know that if your neural network is poor at type inference, then probably your neural network is not really adequate anyway. So it's a benchmark task, because you expect near 100% precision. If your neural network is really good, it should do well. So sometimes there are some ambiguities with type inference as well, but not that much. But yeah, so the idea here is that you don't need any supervision. You just take formulas from natural language, so from human proofs. You are blocking out random subtrees, and then you train these language models to predict the subtrees. And then you evaluate. You don't need to even fine tune. So you just blank out certain types of subtrees, and then you measure whether you ended up with the correct output, or that's something that the human produced. And actually, the really interesting thing is that what we found is that the neural network was really good. It can, for example, 50% of the time predict the exact same assumption that the human used there, which is a really large percentage. But I mean, 50% is just a recall. So if from 8, so if it tries 8 times, then one of them will be the correct one. If you try 1 time, then it only predicts 20-something percent, 25% of the time, roughly. And similarly, for equation completion, we again have some similar, like 40%. No, I think, okay, sorry. For equation completion, we have 50%, roughly 50% of 8 recall. And for assumption completion, we have 35%. But yeah, so, and for type inference, we get close to 100%, so 98 or 99%, depending on the model and encoding. So these neural networks can learn type inference without actually was engineered anything about type inference. So this is how the whole thing works in semantics. So you have like this 2 transformer network, and one is an encoder that sees the whole sentence, input sentence at once. And then the second one sees the output, the missing subtree. So the encoder just sees the context, the tree without the omitted subtree, and then the decoder sees the partial sentence. So it has a trick that it only sees. So for every token, it only sees the previous tokens. So it can learn to predict always the next tokens. And then when you use it, you are using it like a recurrent neural network. So it's like it always looks at the whole previous sequence and then predicts the next token. And that way you can use it as a generative model. So these are tasks that we evaluated the skip tree, and it gave like surprisingly good results. And these are non-trivial tasks, as you could see in the previous. So I'm not sure how many So these are relatively simple cases, but even in those simple cases, it's not trivial for a human even to quickly come up with the right assumptions to make the implication work in a non-trivial way. So yeah, here are the numbers. But so the interesting other thing is that if you train it slightly differently, then you get much, much worse numbers. So you can ask, is it important that you always skipping trees, or you just take the whole formula as a sequence and then you are skipping subsequences? And here you are ending up with, so that gives much, much worse results. So you can see that often your numbers are close to 0 or 5%. You don't get as well. So maybe I stop here. So there are other pre-training tasks, but you can imagine that these models can really well so learn from a lot of data. They can learn interesting mathematical reasoning tasks. And now the task is, how do we use these conjecturing capabilities, these completion capabilities for actual theorem proving? And that's what we are working now. So just so there is another part of this talk, but I will just skip it, that we can also devise synthetic tasks on which we train, and then it improves performance on these tasks even more. But here, let me just give like a small overview of what challenges are there still in mathematical reasoning by neural networks. Is that long-term planning is like, I mean, there are a lot of reinforcement learning work going on, but it's still, they are much harder to apply to mathematics due to the fact that we have this growing knowledge base of statements. So reinforcement learning is not really tailored toward that, but we are working on it. So we can do this retrieval from a large growing database of facts, but we don't the premises. But I mean, integrating it with reinforcement learning is a non-trivial problem. So generating useful sub-expression from experience. So for example, for induction hypothesis is still we don't really know exactly how to do, but these experiments make us very hopeful that that pre-trained by this way, it will give us the right sub-expressions as well. So actually our newest models already produce useful sub-expressions, generate them from nothing basically. And also conjecturing based on experience. So the question is, how do you train a network that creates these conjectures not just like randomly, but creates them from actually playing with the formulas? And then the creating new definitions or concepts is another hot topic, and I think that's the least studied, but I think it's probably one of the most impactful in the long term. And then the other question is, how do you recognize like something is hidden connections between areas, like for example the Lagrange or the moonshine conjectures? You have to play a lot with those formulas and actually really do comparisons on a large scale, and that's probably it's really tough, even for human mathematicians. That's actually the hardest part. And then what we also look into very closely is how we can turn natural language mathematics into formal mathematics automatically. So if we can solve that problem or in conjunction with reasoning, then we could create a feedback loop, create a mathematician AI that can read natural language mathematics and use all the training data we have everywhere, and then learn mathematics and formalize it from scratch. So that is our real dream, a long-term dream. So I conclude my presentation